Hi everyone, it's Prof. K, and today we're going to be talking about reaction yields, which is also described in chapter 7.4 if you would like to read for more information. The learning objectives for this video are to help you learn how to explain concepts of theoretical yield as well as limiting reactants, or in other words, reagents. They can be used interchangeably. And also to be able to derive a theoretical yield for a reaction under specified condition. And from there, calculate a percent yield for a reaction. And in order to do all of this, we need to define the language we're using. So if we want to define the types of yields that we can encounter, the first is a theoretical yield, which is the amount of product that may be produced by a reaction under specified conditions. So theoretical yield is assuming that you use up 100% of your reactants to produce products. How much can you produce? So it's the goal. We don't often do the goal in chemistry, but it is the sort of high bar that we can reach. We can't produce more than our theoretical yield because it's the maximum amount that we can get from a particular set of reactants. Our actual yield is what we actually produce. And so this is the amount of product produced by a reaction under specified condition, even if we think we should have been able to produce more. And the reason why theoretical yield and actual yields can be different can really depend on the context we're talking about. Sometimes we have a reaction that maybe isn't converting to the product all the way, or maybe we're losing some product along the way because of the way that we run our reaction. So in the alum lab, we had some issues with solubility. So that might be a reason why you might get out a lower yield than you'd want for a particular reaction. Percent yield helps us describe the extent to which we succeed at reaching our ideal. So it's the extent to which a reaction's theoretical yield is achieved. So our actual yield as a percentage of the theoretical yield tells us our percent yield. And so it's written as this equation here. And so once we have this language and we're trying to sort of practice using it, we can start to approach problems. So a sample problem here could be, if you have ethylene combustion, that if we burn 20 grams of ethylene with as much oxygen gas as we need, or excess oxygen gas, we find that we produce 40 grams of CO2. And we want to know what percent yield did we achieve. And the first thing that we're told in this problem is that we do produce 40 grams of CO2. And so what that tells us is that we have an actual yield of 40 grams of CO2. And then we have to calculate our theoretical yield. And our theoretical yield is going to be how many grams of CO2 we would have gotten out if this reaction worked 100% and if we used up all 20 grams of ethylene. And so we're going to use some of the tools that we've been learning to do this calculation. So if we start with 20 grams of ethylene, we'll multiply it by the molar, or we'll do some dimensional analysis with the molar mass of ethylene to get the moles of ethylene that we have available to us to do this reaction. And then for every mole of ethylene, we can produce 2 moles of CO2. So this is our stoichiometric factor. And once we know the moles of CO2, then we can multiply it by the molar mass of CO2. And we find that if everything worked perfectly here, we would be able to produce 62.75 grams of CO2, which means that if we go back to our equation for percent yield, we produced 40 grams of CO2 when we could have produced 62.75 grams, which means that we produced 63% approximately of what we might have produced. And so what this tells us is that we were a little bit over halfway to the amount that we hoped we'd get out in what we actually recovered. And so this is how all these different terms interact. And so we'll work through more practice problems where you can implement this. But percent yield is often important to scientists because our actual yield is great. And if we have a large actual yield, that's good. but what we really want is to have as high a possible yield as we can. So we want to get as close to our theoretical yield as possible, because then that means we're operating at a really high reaction efficiency and all of our reactants are being used up to create what we want. So that's good, but it's not something we can always achieve. So percent yield helps us quantify how well we're achieving that goal. And so I used the language excess oxygen gas, and I want to define this concept of an excess reagent and a limiting reagent. So an excess reagent is a reactant that is not entirely consumed. And oftentimes we have this excess reagent in much larger quantities than we might need. So if you're doing a reaction on your benchtop in an open beaker, and that reaction requires the use of oxygen interacting with whatever's in the beaker, chances are, because it's interacting with the oxygen, oxygen is going to be there in as high a quantity as we need. On the other hand, a limiting reagent is the reactant that's entirely consumed, and it's what's keeping us from making more. So it's the thing that we run out of. And a non-science example of this is if I have 3 extra concert tickets and 5 bus seats to potentially get to a concert, and I'm giving these away for free, the limiting reagent for me producing students is the ticket. Even if I have 5 bus seats, I can't take more than 3 students to the concert because we don't have enough tickets. And so if we're talking about an excess reagent, we're going to end up with excess or extra bus seats, and we're going to be limited in how many people we can take by the tickets. So in the end, we're only able to yield 3 happy concert goers, and we're just going to have 2 extra bus seats. So our excess reagent ends up being left over. Now, this could also be true if I had 25 bus seats, but still only 3 tickets. I can still only take 3 people, and I would just have a really empty bus. So the limiting reagent here is the tickets. And if I want to take more students, I need to find a way to get more tickets. And so this is an example of it being used outside of chemistry, but I want to show you how we can use these concepts in the context of a chemical reaction. So if we return to our reaction with ethylene combustion, where we still have 20 grams of ethylene, but this time I put my reaction in a chamber that only has 15 grams of oxygen. And so now what I want to know is which of these reagents or reactants, so I'm using this vocab some more, which of these reagents is going to limit this reaction? So I already calculated a theoretical yield of ethylene in our last problem. And I found that when I calculated that theoretical yield of ethylene, it was possible for me to produce 62.75 grams of CO2. But if I repeat this process where I have 15 grams of O2, and I know that the molecular mass is 32 grams per mole of oxygen, and then for every 3 moles of O2 I use, I can produce 2 moles of CO2. So I have a different stoichiometric factor this time because I'm talking about a different reagent or reactant. And then I use the same molar mass to say that if I had 15 grams of O2, I could produce 13.7 grams of CO2. So if I'm talking about which one will limit me in CO2 production, O2 is my limiting reagent because it's only going to produce 13.7 grams of CO2 before I run out. And then, even though I have extra ethylene, I can't do anything with it because I don't have any O2 to react it with. And so O2 here is the limiting reagent, and our ethylene is my excess reagent. So I'm going to end up with leftover ethylene in my system. And if I want to get more CO2, I have to find a way to add more oxygen. And so the way that I calculated the limiting reagent here, or the way that I determined it, is I used 2 calculations of theoretical yield. So if I wanted to know how much CO2 I produced, you would see that it's the amount produced by CO2 or by the oxygen because we can't make any more than this. So this is the upper bound of our production. So if part B of this problem was how much CO2 can we make, this is a good process by which we can determine a limiting reagent. But there's another strategy that we can use, which sometimes is a little more direct, that I also want to talk about. So instead of using the theoretical yields to determine which one is my limiting reagent, I can also use our stoichiometric factors to directly compare how much O2 I would need for the amount of ethylene I have versus the amount of O2 that I have. So if I calculate the mass of O2 that I would use with 20 grams of ethylene, I can use the stoichiometric factor of ethylene to oxygen to calculate how many moles of oxygen I could use, and thus the mass of oxygen that I would need to use up 20 grams of C2H4. And what you can see is in order to use up all of the ethylene, I need 68.44 grams of O2, but I only have 15 grams of O2, which means that my limit here is going to be oxygen. So I have less oxygen than needed, which makes it the limiting reagent. And so in this way of determining limiting reagent, I only need to relate my reagent to my other reagent using stoichiometric factors. So this might be a more direct way to compare the amounts that I might need in the system and determine the limiting reagents. But if I see part B is going to ask me about the yield of this reaction, then it might be faster to calculate the theoretical yields in the first problem. And so this is two different ways to approach the same issue of determining limiting reagents and how that can potentially affect our yield. And so if we calculate a theoretical yield for this problem, we would have to use the yield that we get for oxygen because it's impossible for us to get up to the yield that we get for ethylene. And so it's important to know which is the limiting reagent and how that influences your yield. So we'll practice more problems like this because it can help us understand what we actually can do in a chemical context instead of what we would sort of like to do or what we might guess we could achieve.